So guys, I guess today we're just so bored that we're gonna learn something called the electron configuration or whatever weird stuff it sounds like. So, what in the world does electron configuration means? We have Google and we can Google it, and alright, of course, there's Wikipedia. Electron configuration. Let's see.
Nah, I'm just kidding.
All you need to know is that what you've learned about the electron arrangement in high school, that the electron arrangement of sodium is 2 add 1 are all lies.
Your life is nothing but lies.
Well, not entirely, but still, today you're going to learn about the truth because it's time, kids. Electron configuration is like how it sounds like. It's to configure the electrons, to arrange electrons. The difference is that you'll learn how to arrange the electrons in an atom in their own shells, subshells. Now, don't get too excited. You still need to know the rules before knowing how to arrange this negatively charged 9.10938.356 times 10 to the power of negative 31 kilogram subatomic particle. But before going into the rules and principles, how about we get to know the history first? Alright, I know. Most of us hates history, but you gotta know about it. I swear, it's something useful. So, who is responsible for coming out with the idea of having to arrange these particles that we can't even see? Now all humankind needs to know how to configure electrons, blah blah blah. It all started with this Danish physicist named Niels Bohr, who had the ambition of explaining the hydrogen spectrum. Let me show you his model of atom. He suggested that in each hydrogen atom, the electrons would revolve about the nucleus in one of several possible circular orbits, and each orbit having a definite radius corresponding to a definite energy for the electron.
Electron in the orbit closest to the nucleus has the lowest energy of electrons in the ground state. Electrons will get excited and jump to a higher energy level of orbits when they absorb any discrete quantity of energy in some manner.
But sadly, this Bohr theory can only be implied on the configuration of a hydrogen atom. So how do we know the electron configurations of other atoms? As you should know, an atom can't be located its exact location, and its momentum cannot be determined simultaneously. Thus, this is where quantum numbers come to the rescue. It is used to describe the probability distribution of electrons in an atom, hence called the way to describe the probable location of electrons. Quantum numbers give the address to know where the electron is situated, just like how we give our house number and city postcode so that people can reach to you. To learn to express the electronic structure of an atom, it is necessary to learn names, symbols, and permitted values of the quantum number. Let us dig in deeper. The principal quantum number is denoted by n. N is the most important quantum number in determining the energy of the electron. The values of n can be any positive integer. The angular momentum quantum number is denoted by L, and it depends on the n value. It can basically determine the shape of the orbital. Orbital is a region where 95% of electrons can be found in an atom. The values are given with letter designation S, P, D, F. Value of L can be 0 or positive integers, but only up to n1. The magnetic quantum number, denoted by M1, shows the orientation of electron in its orbital. The value depends on the value of L, ranging from -1 through 0 to 1. For example, for an electron with L value of 3, the possible M values are -3, -2, -1, 0, 1, 2, and 3. The spin quantum number is denoted by M2 and is related to the spin of the electron on its axis. The value of M2 can only be either -1/2 or 1/2.
So, first thing first. First of all, to configure, you need to make sure you're configuring these electrons according to the electrons' energy levels and make sure they are arranged in shells and subshells, which is the orbitals. You're taking the role of a mother for their ducklings, so check if you got all these rules correct. First rule, the Aufbau principle, where Mr. Aufbau said that electrons are filled into orbitals in sequence or in order of their energy levels. Second rule, Pauli exclusion, where in an orbital there can only be 2 electrons maximum with opposite spins. Not more than 2, you sneaky fox. Only 2. Third rule, Hund's rule, where the most stable arrangement of electrons in orbitals of the same energy level is the one with the greatest number of parallel spins. Oh my god. So, any rules you feel like breaking them because you think rules are meant to be broken? Well, not today, kids. Because if you break them, you can't get the correct electron configuration of an atom, and you'll cry seeing your exam marks because you're too smart not to follow the rules. Let us try to configure an atom. How about we start off easy? How about beryllium? In your periodic table, label this. As you can see, S orbitals have 2 blocks, P orbitals have 6 blocks, D orbitals have 10 blocks, and F orbitals. First, you got to see where the heck is beryllium. Okay, it's there. So now, our starting point is here, where the hydrogen block is located, and we're going to beryllium's house. To get there, we have to go through some other blocks along the way. This is how it goes. The first shell is all filled up, thus it is 1s2. The s orbital on the second shell is also fully filled up, thus it is 2s2. And voila! Beryllium is located on the last block of s orbital, thus it fully filled up the s orbitals, hence the electron configuration of beryllium is 1s2, 2s2. Let's try just a bit harder one. What is the electron configuration of beryllium 2 plus ion? The answer is 1s2. What is the electron configuration of a silicon atom? The answer is 1s2, 2s2, 2p6, 3s2, 3p2. So now it's nap time! In your dreams, because we're going to do some exercise to see if you get the whole idea of this electron configuration thingy. Example 1. What are the values of L that is permitted for an electron when the principal quantum number n is equal to 3? The answer is 0, 1, 2. Example 2. What are the values of n and L in each of the following subshells? A, 2p, B, 3s, C, 5d, D, 4f. The answer for A is n equal to 2, L equal to 1. The answer for B is n equal to 3, L equal to 0. The answer for C is n equal to 5, L equal to 2. The answer for D is n equal to 4, L equal to 3. So now we've learned all the rules, how to configure and all. But the real question is, why are we learning this? As a hobby? Well, not for me. See, how we use a periodic table to configure the electrons. Technically, yes, we use the periodic table as a tool to configure, but the thing is, we are not using the periodic table to configure, but instead, we actually use electron configurations to get a periodic table. Alright, now you can sleep peacefully while I'm gonna chill with my Coke and do things that you kids don't need to know. Goodbye and good luck.